Better. It's like difficult to be optimistic after the previous talk, but I believe that to make the things better, the first step is to see that they are not so good. So we are on the good way, and so I'll try to be optimistic and happy today. I will talk about exploring graphs with Ruby, but first I will try to talk you a little bit about me and what I know about graphs. My name is Eli. I was born in Bulgaria, but I'm now living and working in Spain. I work at the Faber. It's like a very small company based in Bilbao. It's a town at the north of Spain. We develop different products for clients. So we meet them, talk with them about the problems that they have and that they cannot solve with some more generic solution. And we try to develop applications that will solve their problem exactly. So we are going all the way from the talking to the client and seeing what the problem is, then preparing some proposition, then make some fixes to make it fit with their necessity. Then we are installing the product in production, and we make the maintenance also and the support of the product. So we are working in all of the stages of the process. It's very interesting, very challenging, and it's a lot of the time it's fun, not always, of course. So one of our clients is the International Union for Crystallography. I suppose that nobody heard about it before, so it's related with our previous work in the university. I'm a physicist, and I have been working in the field of the material science and solid-state physics. So we have some projects in collaboration with this Union of Crystallography. And one of the projects was the development of a website where the people that are using their products can access the information that normally is printed on paper, like very big volumes with tables, so they can access this information online. And also we added some simple calculations to this information, so it should be easier for the scientists to find what they need. And like on the second stage of this project, we had to develop some more complicated calculations, and one of these was related with graphs. Fortunately, the graphs that we are working with are not very big, so we can work with them using Ruby. It's not very usual. In fact, we know that there can be at most 230 nodes in our graph, so it's very manageable. And we have started first with just traversing the graph to find some information about it. And now, the last year, we have to develop an algorithm for finding shortest paths in this graph. And that is when I started to learn about graph algorithms and started to implementing some of them, trying to understand how this works. And today what I will try to do is like a gentle introduction to graphs. I will not talk about material science, space groups, and crystallography. And I have prepared some simple examples just to show you how the graphs can be used, the data structures that are useful when you have to represent graph data, and also some graph algorithms. When I proposed the talk, I was thinking about talking about different graph algorithms and a lot of examples, how they can be used. But the subject is so large that it's impossible to fit it all in one talk. And so I will speak only about graph traversal algorithms, which are like the basis for the rest of the algorithms that you may use depending on the problems. So, what is a graph? By definition, the graph is just a manner to represent pairwise relationships between objects. The objects can be anything, and the important thing about the graph is that not only the objects are important, but also the relations they have. Just a few comments about the history. It's the first problem that was solved using graphs is from 1736. It's the 7 bridges of Königsberg. Maybe you have heard about it. When Euler solved it, the term graph itself doesn't exist yet. It was used for the first time in 1878. And at this time, it was just a mathematical concept, and the mathematicians were working with it, but it has no practical application. Then in 1936, the first textbook about graph theory have published, but it still was very specific topic. And then in 1969 was when the definitive guide of graph theory was published, and from this moment on, the scientists from different fields can speak about different problems, but using the same language. So that was the moment when the graph theory started to be applied in solving practical problems in different areas. As I told you, in a graph, not only is important the objects that your system is composed by, but also the relations between them. So there is different terminology that can be used to describe graphs. In this talk, I will talk the objects that are related like vertices of the graph, and the relation between them, I will use the term edge. So we will have a lot of vertices that are related with edges. This relation can have direction. So we can have relation between one vertex and another, but not vice versa. It depends on the system that you want to describe using the graphs. What is very important about graphs and what makes them so important is that we have information not only about the objects, but also about the relations. So when you represent a system like a graph, we can see if the relation between two nodes is in one direction. So if, for example, if the vertex A causes vertex B, but not vice versa. And also, we can see relations between different vertices in the graph that are not directly related. So we can see relations between two objects that are not directly related, but they have some relation between them. And this gives us the opportunity to see every one of the objects in the graph in context of the rest that we have. So now that we know what the graph is, how we can represent it when we want to work with these kind of structures. When we are talking about a general graph, there are some data structures that can be used. I have prepared some example for each one of them. This one is the most intuitive, I think, where you have an adjacency matrix. It's a matrix where we have rows and columns that correspond to each one of the vertices. And then in each position, we indicate with 1 or 0 if there is relation between these two vertices. So you can see from the matrix how much relations you have, if there are vertices that have a lot of relations and other vertices that have only a few of them. You can also see that we are using a lot of storage to store zeros, so it depends on the data that we have to represent as graph, if this way of representation is good enough or not. Another way to represent it is if you use a row for each one of the vertices, and then we use columns for the edges. For example, if we have a system with a lot of vertices, but they are not highly related between them, maybe this kind of presentations will need less memory to store the data. So in this case, we are using 1 and -1 to indicate where the edge starts and where it finishes. Another way to represent the graph is using a list of only of the edges, where for each edge we we indicate where it starts from and where it ends to. Again, depends on the data you have. You have to decide if this presentation is good enough. And another way of representing is using the vertices. So for each one of the vertices, you assign a list of its neighbors. So those are the vertices that are related to the vertex. This way of representations can be useful when you have a graph that changes dynamically. So the neighbor vertices of each one of the vertices change rapidly, so this kind of presentation is easy to manipulate. But on the other side, if the algorithm you have to apply needs fast access to the edges, for example, this kind of representations is not very useful. It's like difficult to see, to take a specific edge. These kinds of representation of data are useful up to some limit. Now, in the recent years, the graphs are very popular, but in relation with machine learning and big data, in this case, you cannot, these data structures are not enough for applying the algorithm. So we have to use graph databases. In this case, where the edges and the vertices are like first-class citizens, it's easier to access the information for each one of them. The databases have implemented like very fast graph traversals, and also they permit adaptive data model. Like when we collect a lot of data, normally we don't know what we will collect, so we have to be prepared to adapt our data model to the data that is coming, and the graph databases are the way to save this data. Today I will talk about like simple examples where graph databases are not necessary, and it's like I wanted to show you that you can play with graphs with Ruby, maybe not for something that you have to put in production, but it can be fun to understand how the things work. And if you want to, sometimes you have a problem that can be solved using graphs, although you probably don't have to implement yourself the algorithms because there are a lot of libraries. You can understand how they work, because it's very important to understand how the algorithm works in order to know that this is the correct algorithm for your case, because there is a lot of options and sometimes it's difficult to choose. So if we have to build a class for the graph, we can start with this very simple structure. We have access to the vertices and edges, some initializers, and also we will need a method to add an edge to the graph and to find the neighbors of a given vertex. With this information, we can have our graph and do some traversing on it. For the examples, I will use a adjacency matrix representation where we are working with matrix that has like rows and columns representing the vertices, and each element of the matrix is 0 or 1, depending on if there is an edge relating to vertices or not. The Ruby code I will show you is not especially optimized. I just tried to be very explicit in order to make it more understandable. So with this setup for the graph class, we can start talking about some graph algorithms. During the talk, I will talk only about graph traversal algorithms because it's not enough time to talk about a lot of other stuff, and also because the graph traversal algorithms are like the basis of the rest of the algorithms. No, normally, or the first step in the study, because first you have to see how your graph is, what kind of relations there are, if there is something special about it, in order to decide how to take information from it. So maybe the names of the algorithms will sound like you have already heard about it. The first one is the depth-first search, which traverses the graph from a given source vertex to to the rest of the vertices of the graph. The other one is the breadth first search that does the same but in different manner. And when I will speak a little bit about the extra shortest path algorithm, a star shortest path algorithm, and the k shortest paths algorithm, which is the one that we have used in our application for the union and for crystallography. So the depth first search is a way to traverse the graph from a source vertex to all of the final vertices which do not have more neighbors. So what we do here is like a very simple one. You start with the source vertex, and on which step you have to add to the frontier, which is the list of the vertices that we have to visit next. We add the neighbors of the current vertex, and when we have to take the next one, we just take the last that we have added. So for the frontier, in this case, we will use a stack list. Okay, so the last in, first out. In this case, for this very simple graph, what we will do is like start from the vertex A, which will be our source vertex, and then going through A, C, E, D, and B in order to traverse all the graph. If we draw this step by step, you see that like we are traversing the graph by branches. We go from A to E, then we go step back and visit the neighbors of the node C. This way of traversing a graph is very useful to check how our data is connected. For example, to find if our graph is connected or disconnected. So to search for groups of vertices that are related between each other, but have no relation with other groups of vertices. Also, we can see how much groups of vertices that have relations between them, but no relation, relations between two groups, but no relations inside one group are available. For example, if you have professors that have to give some classes, and you have a set of classrooms that these professors will have to give their classes, you have relation between the professors and the classrooms, but there is no relation between the professors and between the classrooms. In this case, this will be a bipartite graph. Knowing the type of graph that you have helps to choose like optimized algorithm for taking information from this graph, because the general algorithms normally are very expensive. It's difficult to implement them and to use them in production because they need a lot of resources. So it's important to see if your system has some, it's a kind of special one where you can choose one algorithm that is optimized for this kind of graph, and in this way make the calculation faster. Also, you can use the depth first search to see if there are cycles in your graph, if there is a path in your graph that you can follow to start from one vertex and then go back to this one. This is very important characteristic of the graphs that also is necessary if you have to apply some algorithms, because there are algorithms that are fast but do not work with cyclic graphs, for example. So this kind of information is important. One of the applications of the depth first search is the topological sort, which used a lot, for example, to put an order in related tasks, for example. Like when we are creating a rake task that depends on another rake task that by itself depends on another one, when we run the rake command, it has to prepare like an order in which it has to run all the tasks. So all the related tasks are executed before the last one. So this kind of algorithm, if you represent all the tasks like a graph and the relation between them indicate the order in which they have to be executed, and you have a lot of different tasks. If you represent them like a graph and use the depth first search, you can find the correct order for executing them. Another way to traverse the graph, which gives you the shortest path between two vertices, is the breadth first search. Here, what we do is starting from one vertex, and then instead of following a branch from this vertex to the end, what we do is like traversing the graph by layers. So we take the one vertex, we take all its neighbors, and we are visiting each one of these neighbors first, and then the neighbors of the neighbors, and so forth. So here, the algorithm is practically the same, but in this case, the frontier, we add new vertices to the frontier at the end, but on the next step, we take the first one from the vertices. So in this case, the frontier will be a queue. So the first in, first out structure. Okay, so in this case, it's not necessary to traverse all of the graph in order to find the shortest path. If you start from a source vertex and you want to check for a specific target vertex, which is the shortest path, you can stop when you find the shortest vertex, the target vertex, because the way that we are traversing the graph assures us that this will be the shortest path to it. Okay, for the same graph, here we will start by visiting B and C edges, but then we will go to E, which is our target vertex in this case, and it's not necessary to visit the vertex D. So if the information that we want to find about our graph is like the shortest path, it's not necessary to traverse it all. We can use this algorithm to find the shortest path, and also it can be used to check if there is such path in the graph. So with this simple example, it's like very clear what's going on, but if you have like a graph with some more vertices, it can be really difficult to know. So normally this algorithm is used to check if there is a path between two vertices, and at the same time to find the shortest path. Here the shortest path is the path that is related with the smallest number of intermediate vertices. Normally when we are talking about path, we are like thinking about a route where you have to visit different places and you are looking for the shortest path to there, but it can be applied, for example, if you have to compare words. When two words are connected, if there is only the difference between in one letter between these two words. So you can prepare like a graph with all the combinations and see if two words are related and how many changes you have to do in order to go from one to another. And for example, in orthography checkers, it can be very useful. So up to now we have talked about graphs with relations between the vertices that have direction, but nothing more. Like in the graphs, the edges are important part of the information about the graph that we have, so we can assign attributes to them too. When we give like some weight to the edges of the graph, we are talking about weighted graphs. If we have this kind of graph, now here the breadth first search algorithm is not so useful because not always the path that contains the less number of vertices is the shortest one in terms of weight. So in this case, the most famous algorithm is the Dijkstra's shortest path algorithm, where he defines like a cost for a vertex, which will be the sum of the weights of the edges that relate this vertex with the source one. Okay, so while we are traversing the graph, we have to calculate this cost instead of just taking into account the vertices that we have already visited. In this case, we have to change a little bit our class to implement the weight, like information about the edges. It will be an attribute of the edge, and also we need an accessor to take the weight for each one of the vertices. This kind of representation where we have like adjacency matrix, but each element of the matrix will be the weight of the vertex, is called distance matrix. For example, Google has an operational research API where you can ask for a given set of cities, for example, they can give you the distance matrix between all of them. So you can use this representation to apply some algorithms and solve the problem that you have related with this. And the extra algorithm is also very similar. All graph traversal algorithms are very similar. You start from the source vertex and you follow like the frontier to expect the nest of the vertices. The difference is always in how you calculate the frontier, how you calculate which has to be the nest vertex to consider. In this case, the algorithm becomes more complicated. In this case, what we do is for each one of the vertices, we have to calculate the cost that corresponds to it, which will be the distance to this vertex from the source one, plus the weight of the edge that connects the current vertex with its neighbor. And also, during this process, we will save the shortest distance that we have found for each one of the vertices in this distance list. So at the end of the algorithm, we not only know the shortest path between the two vertices that we are interested in, but also the distances to all of the intermediate vertices, which can be important information depending on what we are trying to accomplish. Here, as you can see at the end, the frontier is a priority queue where the elements are ordered always depending on the value of the distance that corresponds to them. So I think that for Ruby there is a library called priority queue that you can use if you have to implement this kind of data structure. It's like a brute force what I have done there. It's like to illustrate what it's all about. And also, during the calculation and the graph traversal, what we have to save is the parent for each one of the vertices that we have already visited. So when we go to the end, we can like go back following these links and find the path itself. For this simple example that I'm using during the talk, you can see that the shortest path will be ACE because it's the distance from the source vertex A to the target E. Following this path will be the shortest one. You can define the distance, the weight of each one of the edges by different manner. It can be depending on your nodes and what the edge represents, what kind of relations. There can be distance, or the weight can correspond to a cost. For example, we have to transport something from one place to another. Like the representation is so abstract, you in fact can fit it to whatever system you have. So this will be like a step-by-step execution of the distance algorithm. And as I told you before, depending on the graph that you have, these general algorithms can be not very optimized for the case. So what a lot of people do is searching for special algorithms that are that depend on the structure of the graph, or that use some additional information that you have about your system in order to make the calculation faster. And the A* search algorithm is one of these cases. In this case, what we have is our graph, but also we have some additional information, so we can estimate the distance between one vertex and the end, and the target vertex. So when we are at some position in our graph, at some vertex, we know the distance from the source to this vertex because we already calculated it and it's the correct value. But then also we have this heuristic estimation that gives us an idea how far we are from the target. So combining these two information, we can find the shortest path faster. Of course, this heuristic estimate, we have to add it to our class and then give it some values at the beginning. And it's important that these values are good enough. So if you sometimes have to do something like this, you have to see how this heuristic function have to be defined in order to assure that you will really find the shortest path for your graph. Here again, the algorithm is very similar to the Dexter's algorithm. The difference is that when we have to calculate the frontier and order its elements in order to have the next vertex that we have to consider, instead of using the distance, we will use this function that is the sum of the distance and the estimated distance to the end. So if we use this algorithm, so we can find the shortest path in smaller number of steps. So depending on the graph that you are working with, it's very fast, much faster than the Dexter's algorithm. And I don't know how I'm going with the time. Just a few words about the shortest paths algorithms. Depending on the problem that you have to solve, maybe the shortest path is not enough. For example, if you have to prepare some routes to visit one place, and the shortest path that you have calculated, it's not available at that moment, you have to have like a plan B. And there are a lot of problems that can be solved or that require information about more than one of the shortest paths. And this is called the shortest paths problems. There are a lot of algorithms because the more complex the problem is, there are more ways to solve it. And the more, like the reference for this kind of problems is the Epstein's algorithm. We have to implement this kind of algorithm in our calculations, and we have used like a slightly modified version of this one. It's a very recent one from 2018. There are a lot of mathematicians working in this area, so new algorithms appear. The advantages of this star algorithm that we have used is that you don't have to traverse all the graph in order to find the shortest paths, and also you don't have to know how much shortest path you want to calculate. It's like going on the fly. You can stop whenever you are happy with the result. If some of you is interested in this, I just ask me afterwards, and I will send you the reference to the article. And well, there are cases when we have a perfect algorithm for finding the solution for our problem. We have a well-described system, but it's not like the implementation of the algorithm is not practical. This is the problem of the traveling salesman, of the traveling salesperson, where we have a person that have to visit a number of cities and following the shortest route. So it's like, okay, we know how to represent this with the graph. We just draw the cities and we calculate all of the possibilities to go through all of them, and then we can find which is the shortest one. The problem is that as the number of the cities gets bigger and bigger, the number of all of the possible routes is like impossible to handle it. So in this case, although we know how to find the correct solution, it's impossible to do it. So we have to find some approximation algorithms, and these are the so-called greedy algorithms, when what we are looking for is just good enough solution. It may be the best one, it may be not, it's enough for it to be good for our case. So, concluding, I hope that if you have to take just a few things from this talk, that will be that there are a lot of systems that can be described by graph. It's so abstract description that you can fit in it a lot of systems, and then apply graph algorithms to analyze them and to obtain some more information about them. The problem is that it's very difficult to implement graph algorithms and to find optimal solution for the graph structure that you have. And there are a lot of frameworks that recently appeared that can be used for solving these kind of problems. But it's important for you to know what they do in order to decide which framework is good for your problem. So with the graphs, like with any problem, you first have to understand the problem, then choose the right representation for your data, depending on the data itself, choose the right algorithm, be patient and enjoy. Thank you.